Hello, everybody. This is a review of atomization, basically. There's three major ways that one can do atomization: nozzles, through nozzles, maybe wheels, and two fluid atomizations. My name is Gary Tatterson. I'm with Chemical Engineering, North Carolina A&T State University. We're going to rely heavily on Lefebvre's book, Arthur Lefebvre, Atomization and Sprays. And here's the errata for his book. Then there is spraying systems, catalogs from spraying systems. Excellent company, and I've lifted some of their literature as a basis for this presentation. They're a great company. I strongly, I don't get any money from them, nor have I ever gotten any money. But they've been nice enough to allow me to share their catalog information with you. Okay, there's another source, a highly mathematical book, and Breitke's book, Robert Breitke, old-timey book. Phenomena of fluid motions, and then there's a whole slew of videotapes on fluid mechanics, whatnot. In fact, this is videos of interest on YouTube, jet breakup, impinging jet dynamics, some really cool stuff, really cool stuff. They can now compute things that I could only imagine when I was younger. Anyway. Again, this was a short course. After each segment, you're asked to list two things that you learned. Yeah, that's sort of get rid of this stuff here. The introductions. There's three ways, and then of course there's probably lots of other ways. But there's a major three ways. It's disintegration by kinetic energy. That's basically pressure drop. And then there's exposure to mechanical energy through a rotating wheel or a rotating vibrating device. And there's exposure to high velocity air with two fluid nozzles, for example. The application of atomization is everywhere. It's huge, okay. Chemical applications, agricultural applications, medical applications. And if we take a look, I'm not sure exactly where this came from. I guess tape 5. You can see there's a whole host of processes that you wish, or in which atomization is used. And if we go to spraying systems, there's a whole bunch of catalog information. Automated spraying, coating, additives, cooling, tank cleaning, airless spray, all sorts of things. Dust control, scrubbers, in case you have a scrubber. Mist, creation of mist washing machines. There's a whole slew of companies as well. Atomization and combustion is huge, obviously. So if we go on here. So I always like to start out with various process objectives, and that way I can zero in on things that are important and things that aren't. You may be interested in high surface area, maybe high coverage. Because you have high surface area of drops doesn't necessarily mean you'll have high coverage. Large area to mass ratios, get them real small, high evaporation and transport rates. You may wish to make a single drop size. You may wish to make uniform drop size. And when I say uniform, say 10 microns plus or minus 1 micron, real spike distribution. You may also want to have high mixing rates, right? High mixing rates. Process objectives become your wish list and also your performance indices. So these process objectives, wish list, performance indices. Process objectives should be understood and clearly stated or understood by everybody. Systems usually have an optimum or often have an optimum. Optimum drop size for spray painting automobiles, optimum spray distance for coating and cooling, optimum drop size for fuel burning, easier light up, lower pollution rates, various items in that. Atomizer selection, you need to know the capabilities of atomizers and know the limitations. And obviously you wish to select the best being consistent reliability with minimum operating problems. Need to know equipment sensitivities to fluid properties, ambient flow conditions, equipment changes. Ideal atomizer does the job, is robust design, flexible design, lightweight, easy maintenance and servicing, low susceptibility to blockage damage. Corrosion, erosion, fouling material build up, free of flow instabilities. And you're looking for good atomization over a wide range of flow rates. This is called turn down ratio. You could possibly also be interested in a good distribution of the drops. Fluid properties, oftentimes you may be spraying slurries, in which case you worry about the solids content. If you worry about solids content, then you've got to worry about the particle size distribution, particle shape, and the ratio drop size to particle size. Maybe you're also interested in wettability. So you need to characterize your slurry much better. Anyway, surface tension comes into play, basically measured with a tensiometer. It's basically force over length. Pressure difference across the interface. Small radiuses, the pressure inside is very large. When R goes to zero or approaches zero, there's a huge pressure rise across the interface. And drops, which were fluid, now are essentially solids. Pressure is so great, they basically are round, very difficult to break. It's very important. It becomes a limit to atomization. Power analysis is kind of interesting. You don't run across power analysis often, but it's a good number to calculate. Basically, gives you an understanding of your nozzle performance, perhaps. You have pressure off across the nozzle times volumetric flow rate. The units on that is power. Or you could have wheel speed, the density, and volumetric flow rate would give you, if you have a wheel, energy per time, basically. Power analysis is very useful in comparing equipment. Should be done on a routine basis. Now, the fluid types are all sorts of things. You have Newtonian, shear thickening, shear thinning fluids, Bingham plastics, false bodies, and viscoelastic fluids. Here's a viscoelastic material. You spread it out in a long string, and then hopefully it will break. But actually, in this case, it may actually spring back due to elastic effects and make a large drop. Not at all what you would anticipate. Then solids, solids is a problem phase. I don't know if you realize that or not. But there's all sorts of solids in the world, far different than liquids. Liquids, you have organic and aqueous. Surface on a liquid is constantly be renewed. The surface on a solid stays permanent. The solid may actually be a trash collector. The chemistry inside the particle may not be the chemistry on its surface. And here we have a few things. We have a sphere, cube. We have needles, and the question is, what's the diameter of a needle? And quickly you find that the important length may be the diameter, or the other important length may be the length of the crystal. So when you get to more complex particle shapes, You may have 2 or 3 lengths that may be important. Diameter of a flake, well, it's an interesting question. Yes, you have the D length, and then you also have the thickness there. And E is supposed to be coming down here, a rough surface. F is, what's F? A twin, maybe. G is a mosaic. H is an aggregate. So you have different types of solids out there. It's an agglomerate. This could be a agglomerate. This could be a tangle. I guess they call it tangle. Now, the difference between those 3 is interesting, to say the least. You also have a heterogeneous up here. The point of the matter is what's on the surface may not be what you think is on the surface. There is indeed supposedly 7 different surface chemistries that may not be inside. Right? So you have one chemistry inside the solid, or if it's a heterogeneous solid, you may have several chemistries inside. And the surface may have 3 or 4 other different types of chemistries happening. So just because you know what you think is this material doesn't necessarily mean you know what's on the surface. What's on the surface depends upon the history of the particle, where its particle has been. Okay. And you have porous, and then you have an aggregate or agglomerate, and then you have layered jawbreaker candies like that. And you have, what is this thing? A partially absorbed, partially activated polymer coating with Q. You do this when you're, say, doing flocculation. You have these strands of long chain polymer molecules, and they attach to each other. Viscosity retards the motion, basically dampens the stabilities. You wind up with larger drops than you thought you would, and typically upper limit maybe 30,000 centipoise. You have non-Newtonian effects can appear. Examples of that would be party string, cotton candy, or angel hair. And of course, you have all sorts of multi-phase effects happening. You may have multi-phase solid liquid where you're spraying a slurry. Demixing in the nozzles may occur. It may not be recognized, but it may occur. Spray pattern goes to drops. Let's take a look at spray pattern. You start out with a sheet and goes into waves or ligaments, and the ligaments finally break down into drop sizes or drops. Now you got to recognize a couple of things. I suspect, looking at this, that the drop size distribution here, is quite different than the drop size distribution over here. And I also have an edge effect coming here. These drops along this edge, for whatever reason, looks to be quite different in size than drop sizes here. And the variable of interest would be how thick is this sheet coming out. That's quite interesting. Here's another view from Robert Brodke's book. You start with a sheet, and the sheet thickness is, again, very important. Sheet thickness tells you the drop size. It indicates what the drop size is. What happens is you have, again, the waves in the sheet that break up into ligaments. The ligaments collapse down into one large ligament. Here is an interesting point here. The curvature, the radius here is small. That means this area right in here is high pressure. Radius is small. Surface tension means acting, it means you have high pressure there. This is lower radii, again, surface tension, lower pressure. So what happens, high pressure fluids, which sit here, move to low pressure regions, which stayed here. So this is a thin spot, but it's drained even further due to surface tension. And so what you have is eventual break-off sitting there. And then you have these large glomerular ligaments going down to a single drop, again by surface tension. And you can imagine if I start throwing in solids of different sizes, how might this change? If it's very fine solids, it won't change much. But if it's, say, needles, it's a different matter entirely. Okay. Anyway, by the way, the information on how particle size affects drop size for needles is probably not a very well studied area. It may be extremely important for your process. Maybe it is, maybe it isn't, but it's certainly not an area that has received attention, probably. So sheets are formed, ligaments form from sheets, wide range of drop sizes produced, no complete theory. That's not necessarily true anymore. Again, you get on some of these calculations that are done with an impinging jet, for example, which is a very important technology. Space shuttle, they have impinging jets. So the calculation of impinging jets become very important. What's interesting is that it's extraordinary what the computer can calculate these days. It's very interesting. You have edge effects that leads to lots of quality problems, non-uniformity, poor coverage, hotspots. You may want to eliminate edge effects. Again, I mentioned this earlier, a slurry, making a sheet. You have particle size to the size of the sheet, thickness of the sheet, ligament diameter, and drop diameter. You can tell me about the particle size, and maybe you do have some sort of information of particle size distribution, but do you know the effects of particle concentration? You can tell me what the size of a Cheerio is, Cheerio cereal, but I seriously doubt if you could tell me the particle concentration in a box of Cheerios or how many particles there are. Then you throw in edge effects or shape effects of the particle. Then you set in a variable on the wetting properties of the particle. And then what type of solid it is, whether it's abrasive solid or a softer solid. You throw in the demixing of the slurries. Interesting. So these slurry sheets where the particle size are going to be changing on you can be quite an interesting and intriguing physics problem. We're interested usually in the solder mean, although the mass median would be interesting. Some drop sizes are easy to visualize, some are indicated by theory. Now, this is a very important concept, this right here. Basically, the surface to volume ratios, okay? This goes throughout engineering. Usually you have a process that's dependent upon the surface, and then you have perhaps the size of the job, which is dependent upon the volume, or a volume process. So you have the ratio of surface to volume, very, very important. And surface is dependent upon surface area. Volume is dependent upon volume. You have surface forces and you have volume forces or body forces. Surface forces are characterized by area, body forces are characterized by volume. Examples, you have electrostatics and surface tension, and electrostatic forces. And volume is dependent upon, say, gravity and magnetic forces. But you ratio those, okay? Length surface to volume ratios. This is extremely important to recognize. Area has one set of physics. Volume has another set of physics. So you may have the existence of two different physics, right? You have two extremes. You have large L and small l, which could generate completely different physics in completely different environments. So I pretend to call this the world of the large versus the world of the small. At large L's, the body forces dominate, surface forces are unimportant. Now, an example of that that's later given to you is, say, a soccer player. Now, a soccer player can kick a soccer ball. There's no problem with that. But you've never seen a soccer player kick dust. The dust will come up into the air when the soccer player hits the dust with his foot. That's true, but it certainly doesn't cross the goal line. It just falls back down. So that's the difference of the one example of the difference of the world of the small versus the world of the large. In spray painting or in sprays, you have large drops and they hit the object or the surface that's being sprayed to. And then you have the mist that's created as well. And that's carried off with the gas stream. So you have this world difference here, area. World of the small versus world of the large. Example, mist and fog. Surface controls the behavior of the object to a large degree. The surface effectively with no mass. Often small particles are flow followers and go where the flow goes. Large particles are volume processes, or volume. Controls, gravity becomes important, surface tension less important. Objects are not flow followers and act differently from the flow. Baseball player hits a home run with a baseball, but no baseball player has hit a home run with a dust particle. So you probably have to have different techniques used for the two different worlds. And I give you the breakdown of the two different worlds. World of the small versus world of large. And the break point may be around 150 microns, maybe 300 microns. Surface volume ratios, effects in engineering. This ratio determines which measurement techniques are used, right? Surface are like heat, mass transfer, volume would be chemical reactions in the volume. T2 laboratories, that's your assignment for this presentation. Go on YouTube and type in T2 laboratories and watch the explosion. You basically had in the problem, you had the heat transfer coefficient, which was L squared. Excuse me, heat transfer surface, which is L squared. And the volume of the reactor, which was L cubed. There was significant, in the accident or the explosion, there was significant L cubed and very minimal L squared. So the reactor they had blew up. They relied totally on one source of cooling, and that fell away, and they tended to overfill the reactor, and that didn't, all kinds of nasty things happened. So you need to pay attention to surface volume ratios and particle size measurements. Case in point, if I look, the upper limit here is about 60 microns, say 160 microns and less. So those are all in the world of the small regime. And then you have the larger ones, which would be the 12,000 microns, 500 microns. So you can see that the measurement that you use is actually indicative of the size. Applications, again, we mentioned carry-off. Carry-off can be a significant loss. You don't want to have too much carry-off. You don't want any for some situations. Basically, the drop doesn't reach the wall. Since they're flow followers, the flow, there's a turn there, right, with flow, and the particle turns with the flow. And larger particles hit the wall. So this, in part, determines wall buildup. And this is particularly important in spray dryers. Spray dryer is often, whether you can use a spray dryer or not, really depends upon whether you have substantial wall buildup. If you have substantial wall buildup, then spray dryer is probably not a good thing to use. You also have L over L squared, which would be, say, drying time to wall area. Drying time, well, this could be L cubed, actually. Particle drying time depends upon the volume, or it could be dependent upon the radius particle. Electrostatic spray painting is kind of cool. You go in and you connect electrically up all the metal in the office. Then you spray a mist and all the paint goes to the metal, coat the metal. Let's see, what else do we have here? Go up here. Okay, let's get into nozzle designs. First off, you got to this is coming again from spraying systems. great company, nice company. Never received any money out of them, and I don't wish to compete with them. I wish them total success. But anyway, first thing you have is a full cone and different types of full cones. And this is the spray pattern that might appear. Excellent, excellent. And then opposed to that are hollow cones, right? Or maybe flat cones, or this would be fan perhaps. And you can see a hollow cone giving you that spray, and a fan, I call them flat nozzles. And then we have, again, specialty type nozzles. For example, this one right down in here gives you a fairly unique. You can have a mister, where there really is not much hitting the surface. And then you have penetration here, high penetration. And then again, you have different patterns laid down. And you can go through the various designs on those. This is, I've taken it from Lefebvre's book. You have potentially a dual-orifice atomizer or a split return atomizer. Here you have an outer orifice and then an inner orifice. You have the primary feed coming, and then perhaps you have a secondary feed. This might be if you're interested in having a turn down in feed rate. I think this can go factor of 100. Yeah, this one always sort of bothers me here. High turn down is duplex to nozzle. Here's a duplex. Variable geometry. Spill return's kind of cool. You have the feed and it doesn't go all out and then it returns back. And then you have spring. For liquids, the spring's fine. But for liquids with solids in it, the spring might be somewhat. Again, I listed this out of spraying systems, really great. The different components to nozzle. It's just not a nozzle. You have the body perhaps, and then you have if you want to filter or pre-filter your spray, good idea for some sprays. So your nozzle doesn't clog. Anything below, what, 0.3 millimeters starts to clog, 0.3 millimeters. And then you have the nozzle tip. Again, what sort of hollow cone, full cone, flat spray. And then you have outlet fittings. I guess this goes out here in case you want to change the shape of your spray. And this is repeated here. Basically, you have maybe something to hold the body, then you have filter, then you have the spray tip, and then you have the retainer. Okay. And spraying systems talk about different types of levels of rain. Anyway, so operating pressures, comments, and different things. Basically, material of construction sits here or here. You have significant nozzle wear with some of these and not so much for others. So obviously it's an important item. And for these, we have, if you were to change different variables, again, this is listed from spray systems. Good group of people again. What happens if you change surface tension? What happens if you change fluid temperature? What happens if you change viscosity? And basically surface tension, no effect, negligible, measurable, increases, decreases, negligible. Anyway. And detecting worn nozzles. We'll get to this a little later as well. And what you have is padenator, basically. We have a whole lineup of different test tubes in here, very small diameter test tubes. And you want to know what the spray pattern looks like. So this is a full cone. Obviously, your spray pattern looks like it's high in the center and tails off. Over here, with a worn tip, you have significant overspray in the center. All right. So we'll talk about patinator a little later. Basically, pressure nozzles work on pressure drop. Pretty simple. You're changing pressure drop into kinetic energy or velocity, basically. It gives you a little table. Basically, you just have a simple hole. Cheap, rugged, disadvantage, narrow cone angle. Diesel engines, afterburners. Orifice limit, 0.3. Again, may need a filter, prevent plugging. 0.3 is the lower plugging size. Not for slurries at all, for smaller sizes. Typically, you're looking for 15 degrees on your cone angle, narrow cone angle. Cone angle is slightly affected by the length of the orifice and the diameter of the orifice. Anyway, so battle off some more of these things here. Need to increase the tangential velocity. You also need to increase the radial velocity if you wish. See, there's axial, radial, and tangential velocities. You want to increase the cone angle, you want to increase the spin. Basically, many studies of fuel injection, gas liquid direction affects atomization. They're going in the same direction, or are they going in the opposite directions? Now then, whenever you're talking about pressure nozzles, you should immediately talk about flow number. Flow number is your friend, basically. And flow number is mass flow rate, divided by pressure drop times density in here, square root. This is important for all nozzles. And what you want to do is constantly monitor your pressure drop and constantly monitor your flow rates, right? Basically, the units on this thing, on the flow number, when you have density included, right, is area, basically. Got to watch out for your units. Units are your friends. But you find out that it's feet squared or inches squared or whatever. Basic variable in operating nozzles, pressure drop, flow rate, and area. Should be a standard calculation routinely done, basically. What you see is mass flow rate is rho VA, density times velocity times area, rho VA. And divided by, now density, pressure drop suddenly becomes rho V squared. So in here, this term is actually rho squared, V squared, velocity squared. Taking the square root gives you rho V. So in a sense, I got rho VA in the numerator and rho V in the denominator. So the left is the area. Now, if I go to spraying systems again and pull off some of their data, right, and do the flow number calculation, I have diameter, just for fun, 0.39 inches. Then I pick off a flow rate, and perhaps I pick off 63 gallons per minute. Right here is the one I'm using, at 200 PSI, which is sitting right there. It's going to operate, here's a picture. I have 200 PSI pressure drop across the nozzle. That's a lot, by the way. Well, 300 PSI. And so let's do a flow number calculation. Here's a flow number calculation, which I could go into detail, but I let you all have that. You got a picture of it here. Anyway, it turns out that the diameter I calculate for flow number is 0.459. And actually the table lists 391. So that ain't bad from a point of view of engineering calculations. In other words, 0.39 inches, and actually I'm predicting the data 0.459 inches, calculating flow number. Okay. So full cone nozzles, okay. You may, with a full cone nozzle, making sure that there is no center vortex. Right? If this thing was allowed to spin in here, I would form a vortex that goes all the way up through. Now, what I do is I add something to induce a spin, but it spins so that it's centrally configured. So there's fluid coming out all radii of this flow circle. So I get a nice solid cone. So thought I'd point that out too. And again, if I do a flow number calculation, diameter, pressure drop, and flow rate, and go through, I get 0.0458 inches as opposed to 0.044 inches. So I highly recommend you make it a habit of calculating your flow number. What happens is, what's tricky about the flow number is it's not necessarily constant, or in fact, it's not constant necessarily. What I'm saying is, as the nozzle is used and worn, the flow number changes because the area of the nozzle changes. Or say the nozzle clogs, right? So that means area is reduced. Suppose the nozzle is worn, so that means area increases, right? Anyway, applications, we have applications of the full cone nozzle, massive data tables. Again, this is from Spray Systems, right? And again, massive tables is the word here. Good stuff, good stuff. They're very nice to publish this sort of information. Anyway, again, I'm going to go to another nozzle, full cone nozzle, do a flow number calculation. Get 0.067 from flow number, 0.063 nozzle. In other words, what I'm trying to say to you is calculate the flow number. Going back to the full cone up here, you can put all kinds of things up in this region. You can put up a filter, you can put up a static mixer, you could, this is free for you to change. Now, you should also recognize if you're spraying slurries, right? Spraying the slurries, that this static mixer may disappear over time, and your nozzle may be worn open, basically, and be just braided away. Abrasion starts around 30 feet a second. 60 feet a second, you have full-on erosion going on. So it gives you an idea of what velocities you should pay attention to. I was in Amsterdam giving a course, and this one young lady had a pressure drop across a valve of 300 psi. And she wanted to know why, after 1 month's time, the valve would disappear, right? At huge pressure drops, you had huge velocities, and at huge velocities, you had significant attrition or significant abrasion occurring. Applications. We'll jump ahead again, nothing much there. Let's try full cone again, just do that. Ah, look at that, we already did that slide, sorry. You get a picture of what you could have upstream. Again, upstream with multiple exits, perhaps. You can have a pigtail. This is a pigtail. Okay, there's your pigtail. You can even have split streams. You have a really fancy exits. I guess this would be a filter. Hopefully it's a filter of some sort. Now, for something looking like that, there's pressure drop across the filter, and then there's pressure drop across the nozzle. There appears to be no nozzle necessarily here. This is off-centered here. The flow comes in off-centered and enters a spiraling chamber and then exits. And this often gives you a vortex right in the center. Since it's off-center, you get a pressure swirl nozzle. Again, pick a combination, do the calculations. Here I give you a spreadsheet. And another one, I guess. You can have square sprays. Of course, it starts out square, and then eventually over time rounds itself off. What you can realize is if I have a square looking like that, I can put another nozzle right there and put another nozzle right there. So I get across the 10 nozzles, I have a uniform application going on, right? Various applications to use this nozzle. Okay, hollow cone, here's the off-center stuff. Flow comes in off-center and leaves. You can see it's off-center here. Not necessarily apparent here. Pressure drop with a swirl, major type, simple, cheap, wide angle, needs a high supply. Pressure supply varies with pressure drop. Applications, cone angle is determined by ratio of spin velocities to actual velocities. Spin velocities may be the radial velocity and the tangential velocity. And you're looking for cone angle varies from 30 to 180. Merges from the orifice angular sheet that forms a conical, hollow conical spray. Turn down ratio, 10 to 1. In other words, the lowest flow is 1, the highest flow is 10. 10 times 1. And again, I get the data tables on it. And again, you wouldn't think these calculations would be, for the flow number, would be unimportant. But if I take a log, I get 0.08 for my flow number calculations. And I got a larger area for the flow number. And I got 10 here, 0.109. Now, the difference between these may actually be the diameter of the vortex, right? See if I can bring up the vortex. Anyway, they have fantastic, again, there's a spin in here, and the spin causes the spray to spread as it leaves. You want it in here long enough so the flow striations are balanced out, but not too much in there. The longer it's in there, the more pressure drop you use up. So there's an optimum length, this length to this diameter. 2.75 times the diameter should be the length of it. It's long enough to spread out the flow striations, but not too long to waste pressure drop. Okay. Hollow cone, right? So that gives rise, you got pressure drop, flow rate, and diameter, but now you also toss in the cone angle that's out there. Okay, so this is a standard angle cone. I don't know what this is for, but anyway. It gives you a composition of what's being in the, again, you have the body, the strainer, the spray tip, whatever that is, whatever you select, and then you have a retainer. So again, the important thing here, this is the idea of the it's off-center feed and gives rise to a spiral. Picking off and calculating flow number on this thing. And I leave that to you, apparently. Fan sprays, right? Good atomization, narrow conical spray pattern, high pressure, cooling and coating industries, different types, type 1, type 2, and maybe there's a type 3, maybe, huh? Orifice in a V, hole in a curved deflection plate, impinging jet on a curved surface. Here's the impinging jet on a curved surface. Here's some examples. Obviously, this is highly directional, right? So it'd be interesting to see what sort of angle is involved with the how this liquid stream, what the angle of flow is. Impingement, here you go. Let's do a calculation and see what the flow number gives us. Bam. Great. So even though it's a flat spray, you find out that the flow number, again, is a measure of the area. See, the Bernoulli equation doesn't really care what sort of area you actually have. I mean, it's pressure drop velocity and height involved, right? So you should wind up with areas that are close to each other, and they are. So you can have a flat spray in different applications, right? One of the interesting questions I was asked one time, I sort of disappointed the guy. He thought he was talking to a college professor, and he viewed college professors as being able to calculate, right, things. And he wanted to know, he had these bottles that he was spraying liquid onto to cool the bottles down. And he wanted to know the relationship between the flow rate and the cooling capabilities. Okay. And in engineering, you should recognize that, yeah, you can speculate on a model and use your equations and calculate things, you know, or you can scrap all that and go out and measure it. So I told him that it'd be very difficult calculations, would be highly speculative in the answer. And the best thing he should do is just measure it. And he didn't like my answer, I guess. Anyway, I thought it was quite amusing. Anyway, no offense to industry. I like talking to industry, but expectations are often best fulfilled with measurements. I mean, there's a whole bunch of stuff involved with, you can't measure. I mean, measure aroma, texture, smell, flavor, all kinds of things that you cannot measure very well. I mean, so there you're even worse shape. You can't calculate it, you can't measure it. So the alternative to this set of circumstances might be that you just speculate on the best equipment you can make or build, and then go from there. Anyway, we have impingement plate. Here's an impinging nozzle, impingement. Then we have foggers. Oh boy, fine mist. Yeah, I was out in the Sedona, Arizona, sitting on a patio. It's hot out there, and they had misters out there where they were evaporative cooling going on, where the liquid would be sprayed out and fine mist and evaporate and cool down the patio that we were on. It's kind of enjoyable situation. In North Carolina, there's concern about how the chickens are going to make it through the hot days. So you can have a dehumidifier or a cooler type situation in their chicken coops. Anyway, what we got here? Hydraulic atomizing nozzles. I guess this thing in here, there must be an opening and closing going on. The fogger. Obviously, I don't want to buy this. I really want to buy stuff that has removable caps. I don't want to buy this big chunk of metal. If one of these go wrong, I have to throw it out or live with the maldistribution. So I always want to design for easy replacement in nozzles because they may actually disappear on you. Okay, if we go here, where were we? I guess I've lost my. There we go. There we. And let's see, you got cone angle. Now you got a real difficulty in specking out this type of. You got to determine how long these things are and how many per circle you got. Oh wait, moly, what a mess. Anyway, accessories. Go down here and see what sort of accessories we have with our nozzles. Strainers, of course, filtration, of course. You may have to have line for air blast, air assist nozzles or gas liquid nozzles. You would have to filter the air as well as the liquid. Quick connect, right? Options. Liquid pressure gauges, solenoid valves, ball valves, check valves. Check valves are useful because you don't want the flow to back up into your other line, right? Liquid strainers, right? Quick connect. Now this is the atomizer that I kind of have a interest in because I think it's kind of cool. Now Lefevre talks about effervescent atomizers, or some people, where that gas comes out of the liquid. Okay. The other way of running that is you feed the gas right down the line, and you're feeding your liquid that you want to atomize. Now this is high pressure. Throw it across the nozzle, and now you have the gas expanding in a significant manner. You could possibly consider what's coming out of this as foam rather than a liquid stream. Okay. And the foam is going to undergo a volume expansion as the pressure drop is reduced. And the foam is liquid won't expand much, but the gas will expand a lot. And you would probably have expanding bubbles coming out of here. Data on such a thing, air to liquid ratio is important. Interesting is 0.1 and 0.2. Now, other data in the other lecture will take this thing up to 2 or 3. Now then, give you a quick quiz on this. You have this data, okay? And the question is, as an engineer, does the data speak to you? Does it say something to you? Okay. And I just toss that out, give you a moment to think. What's this data telling you? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 seconds. Okay, time's up. Okay, what this data is saying is there's a large dripping region here. When the drops get huge, what do you call huge drops? You call that dripping. So out of this nozzle will come drops. And they don't necessarily go flashing out. They could go down here and collect in a pool. One company I was with, they were burning some really bad stuff. And a lot of it, some of it kept on dripping out of their nozzle. And that's because they were running at a very low air to liquid ratio or gas to liquid ratio. So I have a dripping regime up here. Not good for atomization, bad performance. But then these lines actually level off. Okay, and they're not necessarily leveling off here, but further data would have them level off. where everything becomes independent of the air to liquid ratio. In other words, there's a certain air to liquid ratio you have to have. Above that, the lines go flat, and there's no more effect of air to liquid ratio. Here it has a substantial effect going on. Okay, out here, further on out, there would be. Anyway, I thought I'd use my friend rho VA equals rho VA and do, then we use the effervescence for our flow applications. What's the nature of the feed? And I'm talking about 1 atmosphere. Let's see. Basically, the area of the gas to the area of the liquid will be the gas density and the liquid density. Or if I'm at 2 atmospheres, the air to liquid or the gas to liquid is 40. In other words, there's 40 times, the area of the gas is 40 times the area of the liquid. Right? And then at 10 atmospheres, right, density goes up by 10 atmospheres, and I quickly find that the area of the gas is 8 times that of the liquid. At 100 atmospheres, the gas area and the liquid area pretty much equal each other. Right. Anyway, kind of interesting calculation. In other words, what you're doing is you're not necessarily feeding a liquid, but you're feeding foam. Okay, potentially foam. If you got good gas liquid mixing going on in 3 cars. The other kicker would be if you would get rid of the gas, heat the liquid up, put the heated liquid in here, and blow it out. Okay, you have a huge pressure drop. So then the liquid is not boiling here, but as it comes out of the nozzle, it's boiling a lot. So it'd be kind of a cool nozzle as well. Those are probably out there utilized everywhere. It's called a flash drum in the petrochemical industry. So they don't necessarily look at it as a nozzle, but a flash drum has to have a place where you do the flash, right? That's the nozzle. Anyway, what we have here, again, Spray Systems came out with an excellent, excellent booklet on nozzles. In that booklet, they had nozzle maintenance, right? So nozzle maintenance is extremely important. You should check your nozzles. Spray Systems also had huge numbers of videos. Fantastic. They had a video, it was a really funny video, showing all kinds of different flow behavior out of war and tips, right? Let's face it, industry pushes their equipment to the brink of, beyond the brink of failure, actually, to the point where it's operating under failed conditions, where there may be 3 or 4 major streams coming out of one of these nozzles. So change your nozzles. Have a regular maintenance program changing your nozzles. How should you inspect your nozzles? A common problem, erosion and wear. Then you have corrosion, and then you have clogging, and then you have caking, and then you have temperature damage. Of course, we have improper assembly. It's because all kinds of bad stuff. And accidental damage. What I find fascinating is this clogging or caking phenomena. I can take a very wide orifice and I can feed a very fine slurry through that thing. And one small particle builds up on another small particle, which builds up on another small particle, which builds up on another small particle, and reduces the flow area. You may think that a high pressure drop is going to save you from clogging. Well, maybe it does, and maybe it doesn't. It's kind of interesting. See what we have here. How to check. Okay, basically you're checking flow rate versus pressure drop. What you're doing is checking or getting the measurements for the flow number, right? Product quality and application results, you check the flow rate and pressure. Right there is the flow number. Then you check the pattern, right? And then you check alignment. Alignment's really neat, right? That's where you have your padinator involved. Let's dig up that padinator, right? Go jumping forward to our padinator. Excuse me, padinator. Somewhere I have my padinator. Oh, there we go, padinator. Sorry, hold on. Oh, I don't have it. Somewhere is my padinator. There's my padinator. Da, 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 da. Everybody should have a padinator, right? If you have a spray here, you got a collection of test tubes here, full cone, hollow cone, flat spray cone, don't matter none. You want to know how it looks, how the distribution of the liquid is collected up. Padinator, how do you buy one? I don't know. You could probably get one of those poor college interns there and have them build you one. Test rig for a padinator. You take out your nozzles from your equipment, run them through your padinator and see what you got. You got poor performance. So anyway, let's go back to where we were, if I can find it. Here we go. So everybody gets a padinator. Padinator. Okay, again, flow rate, pressure drop gives you flow number, spray pattern from the padinator, and nozzle alignment. Material of construction, increasing, this is, I think, given to you earlier. If I increase operating pressure, what happens? Increase specific gravity or the density, what happens? Notice negligible. Increase in viscosity, there's some increase in fluid temperature, increase in surface tension. No effect. Negligible. Increases, decreases, no effect. Negligible, sorry. Then we have more on density, more on temperature, and more on surface tension. Material of construction. I like this concept of using sapphires. You know, kind of cool. Major drawbacks to these atomizers. One, they're high pressure drop. Doubling the flow rate requires fourfold increase in pressure. This limitation leads to the development of a wide range of atomizers. And changing out atomizers to handle higher flow rates, probably. Have an atomizer with a high turn down ratio, there you go. I don't know, right offhand, I don't have a vendor for high turn down ratios, except probably the US government. If you take a look at your car, you know, you're going 10 miles an hour and you then press on the accelerator, you're changing the flow rate, so you're speed up. And so that's an example. Large turn down ratios for engines and burners. Other types of nozzles seal favor for those. Anyway, drop size information. It's kind of interesting. If I start looking at, well, why don't we stop here and then pick it up a little later. We'll start by bringing up drop size information. I hope you have enjoyed this. I hope it's useful to you. I plan 2 or 3 more videos. One video on drop sizes. Then I'll go into wheels, and then I'll go into two fluid nozzles, and again, drop sizes. There's a combination of Lefebvre's book, which is an excellent book, and it's filled with data, and also spray systems. When I say Lefebvre's book is filled with data, usually small scale, okay? Nozzles, fortunately, are small scale. The relatively small size changes in size. Anyway, I'm going to end the meeting. I hope you enjoyed it. And again, there's 2 or 3 more videos coming down the pike on atomization.